Hello students. So let's continue with our NCERT chapter 8, which is aldehyde, ketones and carboxylic acids. So today is the theory part 9 and the section which we will cover today is section 8.9 to 8.9.1. This is the disclaimer. So what is the objective of today's lecture? After attending this lecture, you will be able to correlate the chemical reactions of carboxylic acids with their structures, and you will be able to understand various factors affecting the acidity of carboxylic acids and their reactions. Now for your reference, I have mapped the NCERT sections which we will cover today. So we will cover section 8.9, which is chemical reactions, and section 8.9.1, which is reactions involving cleavage of OH bond. So let's begin with today's topic of reaction involving cleavage of OH bond. So first we are going to discuss the reactions of carboxylic acids with metals and alkalis. So carboxylic acids, they react with electropositive metal to evolve hydrogen gas and form salts. Okay, so they react with these electropositive metals and evolve the hydrogen gas and form salts. Now this is very similar to how acids react with metals, where the metal displaces hydrogen from the acid. So it is very similar to this thing. So if we look at this chemical equation, so this is showing the reaction of carboxylic acid with sodium metal. Okay. So if you see the reactants, there are 2 molecules of carboxylic acids and you have 2 sodium atoms, which produces 2 molecules of salt, which is sodium carboxylate salt, and hydrogen gas. So this is a type of a this is a typical acid metal reaction. So now carboxylic acids, they also react with alkalis such as NaOH, which is sodium hydroxide, and KOH, which is potassium hydroxide. So these reactions, they are important because they show how acids, they can be neutralized by bases forming salts and water. So if you look at this equation between a carboxylic acid and sodium hydroxide, so the acid over here, okay, which is carboxylic acid, they reacts with the base, which is sodium hydroxide, to form a sodium carboxylate salt and water. So this is a typical example of an acid-base neutralization reaction. Now carboxylic acid, they can also react with weaker bases like carbonates, which is Na2CO3, and bicarbonates, which is NaHCO3. Okay, so if I talk about these reactions of weaker bases with carbonates and bicarbonates, so they are quite useful in various applications, such as in baking, where these bicarbonates, they are used as leavening agents. So in these reactions with carbonates and bicarbonates, the carbon dioxide gas is evolved. So this is quite similar to the fizzing you see when you mix baking soda with vinegar. Okay, so if you have seen it at home, when you mix baking soda with vinegar, you see a fizz coming out. Okay, so this is another kind of an acid-base reaction. So the evolution of this carbon dioxide gas is a common test to detect the presence of a carboxyl group in an organic compound. So this is a practical application in laboratory which is used to identify the unknown substances. So if you look at this reaction of carboxylic acid, this is a carboxylic acid with sodium bicarbonate, which is NaHCO3. So the products are sodium carboxylate salt, which is RCOONA, and you will see water and carbon dioxide. Okay, so this reaction, it is very often used in qualitative analysis to confirm the presence of carboxylic acids. Okay, so these are the reactions of carboxylic acids which we saw with metals, with alkalis, and with weaker bases like carbonates and bicarbonates. Now we will start with the topic of dissociation and acidity constant. Okay, dissociation, which is Ka, and acidity constant, which is pKa. So carboxylic acids, they dissociate in water. This means that they break apart into ions when dissolved. And this is also a key characteristics of acids. So as carboxylic acid dissociate, they form a resonance stabilized carboxylate anions and hydronium ions. So as they will dissociate, you will see there will be a resonance stabilized carboxylate anions. So this resonance stabilization, it helps to spread out charge, which makes the anion more stable. So if you look at this particular image, okay, here you will see the dissociation process of carboxylic acids. So this is a carboxylic acids. When it dissociate into water, it gives hydronium ion, which is H3O+, and this is the carboxylate anions. And these carboxylate anions, they are resonance stabilized. Okay, you can see the spread of this charge, of this negative charge, which is stabilizing the anions. Okay, so this is the resonance stabilized carboxylate anions. Now if we see the equilibrium constant here, KEQ, this is the equilibrium constant. So this equation, this shows the relationship between the concentration of ions and the molecules which is involved in the dissociation of carboxylic acids. So if you take this as your reactants, where carboxylic acids react with water to give hydronium ions and carboxylate anions. So when we write equilibrium constant, on the numerator side we write the concentration of the products divided by the concentration of the reactants. So on product side I have hydronium ions, and you will see this resonance stabilized carboxylate anions. Okay, and which is divided by the concentration of water and carboxylic acid. So here KEQ, this is the equilibrium constant. So this equilibrium constant, it is the measure of extent to which a reaction proceeds to form products at equilibrium. Okay. Now, as we know that this KEQ, which is a measure of the extent of chemical reaction, we have already seen that this is equal to the concentration of hydronium ions into the concentration of carboxylate anions divided by the concentration of water into the concentration of carboxylic acids. So the concentration of water is considered constant. Why? Because it is present in large excess compared to other components. So we do it basically to simplify our calculation and understand the reaction. Okay, so here we are taking the water, the concentration of water, which is this H2O, as constant. So when this combines with KEQ, it produces another constant Ka. That is, when this concentration of H2O combines with another constant which is KEQ, it produces another constant which is Ka. So Ka is equal to KEQ into the concentration of water. Okay, and this is equal to the concentration of H plus ions into the concentration of RCO2 minus ions divided by the concentration of carboxylic acid. Okay, so this KEQ into this equilibrium constant into this H2O gives another constant which is Ka, and Ka is the acid dissociation constant. So this is crucial for determining how easily acid donates its protons in a solution. Okay, we know what is a good acid. A good acid easily donates its protons in the solution. So we see that the strength of an acid This is generally indicated by its pKa value. Okay, so this is a convenient way to compare how strong different acids are. Okay, so we generally determine the strength of an acid by its pKa value. So this is a very famous formula which you all must have studied in equilibrium chapter of class 11th. So this formula says that pKa equals to negative log of Ka. So this relationship is quite important if you have to calculate the pKa value from the dissociation constant Ka. Okay, so if you know the value of Ka, you can find the value of pKa. So if we look, now we will see the pKa values for different acids. So the pKa value of hydrochloric acid is to be -7. Now see, it is -7. This indicates that the hydrochloric acid is a very strong acid. Next, if we talk about trifluoroacetic acid, then this is the strongest carboxylic acid. So the pKa value is 0.23. Okay, so this shows that this carboxylic acid, trifluoroacetic acid, is also a very strong acid, but it is not as strong as hydrochloric acid. Similarly, if we talk about the pKa of benzoic acid, then this benzoic acid pKa value is 4.19. So this suggests that this benzoic acid is weaker than both hydrochloric acid and trifluoroacetic acid. Now we have learned that smaller the pKa value, stronger is the acidity. Smaller is the pKa value, stronger is the acidity. So if the pKa value will be small, the acidity will be stronger. It will be a stronger acidity. So here if we see strong acids, they have a pKa value less than 1. Okay, so can you guess an example of this category? Right now we only discussed, that is hydrochloric acid. So the pKa value is less than 1. Similarly, if I talk about moderately strong, then they have a pKa value between 1 and 5. Like you can put benzoic acid in this category. If I talk about weak acids, then they have a pKa between 5 and 15. So these acids, they are less likely to donate protons compared to stronger acids. See, it is between 5 and 15. And if we talk about extremely weak acids, they have a pKa value greater than 15. So these acids, they are very weak and they do not dissociate easily in the solution. Okay, so here we talked about the pKa value and we saw pKa values of different acids, and then we saw that smaller the pKa, stronger the acidity. Now we will discuss about the acidity of carboxylic acids. So we will see about the carboxylic acids. Then carboxylic acids, they are weaker than mineral acids. Mineral acids like hydrochloric acids and sulfuric acids. Right now we only saw that these acids, their value is -7. Okay. So this means that they do not protons as readily as these stronger acids. However, the carboxylic acids, they are stronger than alcohols, which have a pKa value around 16. So they are weaker than mineral acids, but they are stronger than alcohols. This indicates that the carboxylic acids, they can donate a proton more easily than alcohols. Additionally, carboxylic acids, they are more acidic than phenols also. Okay, so they are stronger than alcohols and they are more acidic than phenols. This means they are more likely to donate a proton compared to phenol. Now we will explore, or we will see, that why the carboxylic acids, they are more acidic than phenols. Okay, so first we will see the acidity for carboxylic acid, and then we will see for the phenols, and then we will compare. So when a carboxylic acid, it donates a protons, it forms a conjugate base. Okay, whenever an acid donates a protons, it forms a conjugate base, and here in this case it is a carboxylate ion. Okay, so if you see that if COOH donates a proton which is H plus, it forms a carboxylate ion which is RCOO minus. Okay. Now the negative charge on the carboxylate ion it is delocalized over two oxygen atoms. If you say here two oxygen atoms, so negative charge is delocalized equally over two highly electronegative oxygen atoms. This means the charge is spread out, which contributes to the stability of the ion. Next, the resonance structures of the carboxylate ion, they are equivalent. Equivalent means they are giving extra stability. And this high level of stabilization is a reason that why carboxylic acids, they are more acidic than phenols. Okay, so thus the carboxylate ion is highly stabilized. If you look at this picture over here, this is the resonating structures in the carboxylate ion. Okay, so you can see over here that the negative charge, it is delocalized equally over two highly electronegative oxygen atoms. Okay, so this gives this resonance structures, you can see they are equivalent, which gives its extra stability. Thus, these carboxylate ion is highly stabilized. Now, if we talk about the Y phenols, earlier we compared for the carboxylic acid. Now we will see for the lower acidity of phenols. So when phenols, they donate a hydrogen ion, they form a conjugate base, which is a phenoxide ion. Okay, phenoxide ion C6H5O minus. Now the ion has a negative charge that is spread out into the aromatic ring. Okay, we will see that oxygen, this has a negative charge and this is spread out in the aromatic ring. But there is some problem. The resonance structures of the phenoxide ion, they are non-equivalent. This means the way that the negative charge is distributed is not uniform, and that affects the stability of the ion. So when you see the resonance structures, it places the negative charge on the carbon atoms, and these carbon atoms are less electronegative than the oxygen. So this is not ideal because carbon does not hold negative charge as effectively as oxygen can, because carbon is less electronegative. Okay, so because of this non-equivalent resonance structures and the placement of the negative charge, the delocalization of the charge in the phenoxide ion is less effective. This means that this ion is not as stable as it should be or as it could be. So as a result of this lack of delocalization, the phenoxide ion is less stabilized. Now, if you look at these resonating structures of phenol, this oxygen has a negative charge and this negative charge is delocalized into the aromatic ring. But if you will see that some structures, this places a negative charge on the less electronegative carbon atoms. As you can see here, the negative charge is placed on the less electronegative carbon atoms. Okay, so therefore the delocalization is less effective compared to the carboxylate ion. Okay, so hence phenoxide ion is less stabilized. Okay, now we will see the effects of substituents, or how substituents, they can influence the acidity of carboxylic acids. So substituents, they are directly they are attached to the main carbon chain, and so they can play a significant role. So substituents, they can affect the stability of the conjugate base, which in turns affect the acidity of carboxylic acid. Okay, so they affect the stability of conjugate base and affecting the acidity of carboxylic acids. So the conjugate base, how is conjugate base formed? I hope you know. It is when the acid donates or protons. Okay, so its stability is crucial for determining how acidic the compound is. Now, if I talk about electron withdrawing groups, okay, which is known as EWG, this is how it is abbreviated. So these groups, they can increase the acidity of carboxylic acid by stabilizing the conjugate base. So it makes it easier for the acid to donate a proton. Okay, so these groups, they help stabilize the conjugate base by delocalizing the negative charge. Okay, and this can happen through inductive effect, where the electron withdrawing group pulls the electron away or through resonance effect. So it can be through minus I effect or minus R effect. In R effect, the electrons, they are spread out over multiple atoms. Okay, so you can see that the delocalization of the negative charge, they can occur by inductive or the resonance effect. So if you look at this particular image, that if an electron withdrawing group is attached to this carboxylate anion, so this electron withdrawing group stabilizes the carboxylate anion and it strengthens the acid. Okay, so it increases the acidity by stabilizing this conjugate base. Okay, and you can see that here the it will delocalize negative charge by inductive or the resonance effect. Now if we look at the increasing order of acidity among different substituents, so here you can see the order of increasing acidity. So phenyl has the lowest, okay, then comes the iodine, bromine, chlorine, fluorine, cyanide, NO2, and then this is trifluoromethyl. So you can see that trifluoromethyl, this is an electron withdrawing group and it increases the acidity of this CF3 is attached to a carboxylate anion, then this will increase the acidity more as compared to rest of them. Okay, so this is the increasing acidity order. That means CF3 is highly acidic and phenyl is least. Okay, now we will see next about the electron donating groups. So these groups can affect the acidity of the carboxylic acids. Okay, so these electron donating groups, they decreases the acidity by destabilizing the conjugate base. Electron withdrawing groups, they were stabilizing the conjugate base, but they are destabilizing the conjugate base. This means that when these groups are present, the carboxylic acids, they are less likely to donate a proton. Okay, so if you see that if electron donating groups are attached to a carboxylate anion, so this weakens the acid. So if it weakens the acid, then then we will see that it does not readily donates its proton. That is, it decreases the acidity. So if we look at the decreasing order of acidity on the pKa values, then look at the image which is shown over here. Okay, so see how the structures and the substituents, they affect their acidity. Okay, so if you see over here, CF3COOH is strongest. Okay, because if I talk about CF3, then CF3 is a very powerful electron withdrawing group. And if I talk about other halogen substituted acids like CCl3, COOH or CHCl2, COOH, then they are stronger as compared to the formic acid. Okay, whereas if the nitro and cyano groups, they also withdraw strongly, hence these are also strong acids. Now if I talk about simple alkyl groups, okay, like CS3 or C2H5, then they are electron donating. Because they are electron donating, so they are considered as the weakest acid. Okay, and you look over here of this phenyl, which is C6H5COOH, then this is weaker than the formic acid, because this C6H5, it donates the electrons through resonance into COO-, which is destabilize it. Okay, so this is that CF3COOH is the strongest and CS3CH2COOH is weakest, because this alkyl group donates the electron density. Okay, so if it is donating the electron density, then the OH bond will become less polar and hydrogen will not be released easily. But if I talk about CF3COOH, then this withdraws the electron density, which stabilizes the conjugate base and makes the release of a proton easier. Now we will see the effect of sp2 hybridized carbon, which is attached to carboxylic acid. So direct attachment of phenyl or vinyl group, they increases the acidity of carboxylic acid. So if phenyl or vinyl group is directly attached to a carboxylic acid, it will increase the acidity of carboxylic acids. So the reason is sp2 carbon of phenyl or vinyl group is more electronegative than sp3 carbon. Okay, we know that sp2 carbon is more electronegative as compared to sp3 carbon. So because it is more electronegative, so the electronegativity, it pulls the electron density away from the carboxyl group. Okay, so if it is taking the electron density or pulling the electron density, so it will increase the polarity of OH bond. And if polarity of OH bond is increased, then it is easier to release a proton. Proton can be released easily. So that is why if a phenyl or vinyl group is directly attached to a carboxylic acid, it will increase its acidity. Okay. Now we will see the effects of substituents on aromatic carboxylic acids. First, we will see the focus on electron withdrawing groups. Okay, so we will see electron withdrawing groups on phenyl ring. So electron withdrawing groups, they increases the acidity of the aromatic carboxylic acid. So it makes it easier for the acid to donate a proton. Okay, so electron withdrawing groups, they stabilize the carboxylate ion through inductive and resonance effect, that is through -I or -R effect. And if I talk about electron donating groups on the phenyl ring, then they have opposite effect compared to electron withdrawing groups. Okay, so electron donating groups, they decreases the acidity of the aromatic carboxylic acid, that is they make it harder for the acid to release a proton. So the electron donating groups, they destabilizes the carboxylate ion through +I or +R effect, and this destabilization explains the decrease in acidity. So if you look at this particular figure or image, you will see over here you have 4-methoxybenzoic acid, that is 1, 2, 3, 4. On fourth carbon, a methoxy group is attached. This is a simple benzoic acid and this is 4-nitrobenzoic acid. And look at the pKa value. The pKa value of this is 4.46. It is 4.19 and this is 3.41. So smaller the pKa value, strongest the acid is. If you see in this 4-nitrobenzoic acid, you have a NO2 group, which is an electron withdrawing group. So we have seen that electron withdrawing group, they increases the acidity. That is, they stabilize the carboxylate ion by -I or -R effect. Whereas if I talk about 4-methoxybenzoic acid, then this OCH3 group is an electron donating group. So this decreases the acidity because it destabilizes the carboxylate ion by +I or +R effects. Okay, so this is the effect of substituents on aromatic carboxylic acids. Now we will arrange the following compounds in the increasing order of their acidity. So you have been given 2, and 3. Okay, so you have to arrange it in the increasing order of their acidity. First, let's see what is first. It is CH3, CH2, CHBr, COOH. Okay, so here you can see that Br over here is attached to second carbon, and here Br is attached to 1, 2, 3, third carbon. Okay, here there are to this CH, 2 methyl groups are attached, and here it is simple CH3, CH2, CH2, COOH. Then over here you see this is benzoic acid, this is 4-nitrobenzoic acid, this is 3,4 dinitrobenzoic acid, and this is 4-methoxybenzoic acid. So you have to arrange it in the increasing order of their acidity. First, let us see the first part. First, if I talk about carboxylic acid ionization, then if this is a carboxylic acid, okay, then this shows that a carboxylic acid, which is RCOOH, it loses a hydrogen ion to become a carboxylate ion, which is RCOO-, and H plus is released. Okay. So the resulting carboxylate ion which is formed has a negative charge. So this is COO-. So the negative charge, it is crucial because the stability of this ion, it affects the acidic strength. That is, more stable the carboxylate ion, stronger will be the acid. So we will see the effects of substituents on stability and acidic strength. Okay. So if I talk about groups with a positive inductive effect, so the groups that shows plus I effect, they tend to destabilize the negative charge on the carboxylate ion. So this destabilization results in the decrease in acidic strength. Okay, and if I talk about a negative inductive effect, that is group which shows minus I effect, they stabilize the negative charge on the carboxylate ion. So this stabilization, it increases the acidic strength. Okay, now if we see the examples of plus I and minus I effects, then the CH3 group, if I talk about this methyl group, this shows plus I effect, means it can donate the electrons. Okay, so if this donates the electrons, then what will happen? It will decrease the acidity. Similarly, if I talk about Br, the bromine group, it has minus I effect, means it can withdraw the electrons. So this electron withdrawing property, they can make the compound more acidic. How? By stabilizing the negative charge on the conjugate base. Therefore, the acids containing bromine, they are stronger acids than those with methyl group. So if there are bromine, then these will be stronger acids compared to the one with a methyl. Okay, this is because the electron withdrawing effect of bromine, it stabilizes the conjugate base, which makes the acid more likely to donate a proton. So right now we compared between the groups in which bromine is present and CH3 is present. So we concluded that if CH3 is present, then they are considered weaker acids. Now we will compare the acidic strength that is of the isopropyl group. So the isopropyl group, they have stronger plus I effects than N-propyl group. So this isopropyl group over here, okay, they have a stronger plus I effect. Okay, and this N-propyl group, they have less plus I effect as compared to the isopropyl group. Okay, because if you see over here, that to this carbon, two methyl groups are donating its electron density. So if I talk about the acidity order, if we compare the acidity order of these two groups in which there is one isopropyl group and in this there is N-propyl group. So the acidity of this if I talk about, then isopropyl group, they have stronger plus I effect. So if they have stronger plus I effect, then their acidity will be lower because this will destabilize the carboxylate ion. So if the acidity order of this N-propyl group will be more as compared to this isopropyl group. Okay. Now if we see the effects of position on minus I group. So if we see that here there is difference in the position of the Br. Okay, so minus I effect decreases as the distance from the carboxylic acid increases. Okay, so that means that closer the bromine is to COOH group, the stronger will be its effect on the acidity. Okay, so if you see over here the bromine is attached to second carbon and here bromine is attached to third carbon. So I said that where bromine minus I effect or inductive effect decreases as the distance from COOH increases. So here the distance is increasing. So that is, this acidity will decrease. So this compound will have more acidity because this bromine is more close to COOH group. Okay. So if we compare the overall acidic strength, then this one in which a bromine group is attached will have a more acidic strength compared in which no bromine group is attached. And if bromine is close, here bromine is close, so it is having more acidic strength. Compare here bromine is far than the carboxylic group. And if I compare about this isopropyl and simple propyl, then this N-propyl will have less plus I effect. So that is why this is more acidic compared to this isopropyl group. Now we will see the next part. It is the effect of substituents on aromatic acids. So electron donating groups like methoxy, which is the OCH3 group, this decreases the acidic strength. Okay, so if I talk about electron donating group, then they destabilizes the carboxylate ion and it decreases the acidic strength. Whereas if I talk about electron withdrawing groups like nitro groups, then they increase the acidic strength because they stabilize the conjugate base. So more electron withdrawing groups means stronger acid. If electron withdrawing groups are present more than one, that means it will be a stronger acid. So if we talk about dinitrobenzoic acid 3,4, then in this we will see that two nitro groups are attached to benzoic acid. Here only one nitro group is attached. So that is why 3,4 dinitrobenzoic acid is more acidic compared to nitrobenzoic acid. Whereas in this benzoic acid there is no substituent attached, so we place it in middle. Then comes the 4-methoxybenzoic acid. In 4-methoxybenzoic acid, we have a OCH3 group, which is an electron donating group. So this electron donating group decreases the acidic strength because it destabilizes the carboxylate ion. So that is why this 4-methoxybenzoic acid is least acidic, and 3,4 dinitrobenzoic acid, which consists 2 nitro group, is most acidic. Okay, so I hope this is clear to you. So thank you students for your attention. I hope the concepts which we discussed are clear. Hope you all have a good day. Thank you.